The high-pressure turbine of a low-bypass turbofan is one of the harshest mechanical environments on Earth. To achieve the thrust-to-weight ratios required for modern military aircraft, the gases entering this section must exceed 1,500 degrees Celsius. The engineering paradox is that the metals used to build the turbine blades melt at temperatures hundreds of degrees lower than 1,500 degrees. The primary barrier to building a world-class fighter engine lies right here in the hot section, not in the aerodynamic design of the compressor. Mastering military aviation strictly requires mastering the atomic-level manipulation of materials. In 1986, India launched the GTX-35VS program, better known as the Cavary engine, designed to power their homegrown light combat aircraft, the Tejas. The target was specific: a flat-rated, twin-spool engine capable of delivering 81 kilonewtons of wet thrust, meaning thrust generated with the afterburner engaged. The Cavary consistently fell short of the 90 kilonewton thrust ryant eventually set by the Air Force, and the prototypes exceeded weight limits. This failure was concentrated almost entirely in the high-pressure turbine module. The Cavary struggles demonstrate exactly why blueprints alone cannot build a jet engine without a highly advanced metallurgical ecosystem to support it. Inside the hot section, turbine blades spin at up to 15,000 revolutions per minute, while submerged in a 1,500-degree gas flow. This combination of extreme centrifugal force and intense heat causes a phenomenon known as creep deformation, a process where the metal stretches over time. Under a microscope, traditional polycrystalline alloys consist of a lattice structure filled with chaotic intersecting lines called grain boundaries. Under continuous thermal stress, these boundaries act as fault lines where tiny cracks initiate and expand. This exact material failure mode forced early iterations of the Cavary engine to halt testing. The blades simply could not withstand the operational stress. The solution to creep deformation requires eliminating those grain boundaries entirely by manufacturing the blade out of single-crystal nickel superalloys. Through vacuum investment casting, molten nickel superalloy solidifies in one uniform direction, maintaining a perfectly controlled temperature gradient so no internal boundaries form. Only a fraction of nations possess this manufacturing capability. India's Defense Metallurgical Research Laboratory finally achieved domestic production of single-crystal turbine blades in 2021. Overcoming the physical limits of metal requires engineering materials at the atomic level. Even a flawless single-crystal superalloy will eventually melt in a 1,500-degree environment without active intervention. Engineers solve this through active cooling, bleeding off between 1% and 3% of the relatively cooler air from the engine's compressor. This bleed air routes through complex serpentine channels cast inside the hollow turbine blade. The air exits through microperforations on the surface in a process called film cooling, creating a thin, protective buffer envelope around the exterior metal. Creating these internal channels requires extreme precision, relying on electrical discharge machining to achieve submicron tolerances. The final protective layer applied to the blade is a thermal barrier coating, typically made from materials like yttria-stabilized zirconia. These porous ceramic coatings insulate the metal, but they are highly prone to spallation, or flaking off, when subjected to heavy oxidation over time. A modern turbine blade operates as a complex, actively cooled thermodynamic machine in its own right. Possessing the blueprint or CAD file via tech transfer does not equate to possessing a functional engine. High cycle fatigue from continuous vibrations and hot corrosion from ingested contaminants cannot be perfectly simulated in software. A new engine requires over 10,000 hours of physical endurance testing against specific mission profiles to prove it is safe to fly. This demands a massive, capital-intensive physical testing ecosystem, including high-altitude testbeds and automated spin facilities. India lacked this complete infrastructure, which forced the Cavary project to rely on Russian facilities, mounting the engine on an IL-76 flying testbed for high-altitude validation. Physical validation in aerospace is an iterative, closed-loop process. The testing itself is the development. Without a domestic testing ecosystem, discovering and fixing a point of failure takes years instead of weeks, which directly cripples development timelines. When you reassemble these components, moving from the cooled single-crystal blade back to the complete turbofan, the scale of the engineering challenge becomes clear. Despite the hurdles, the Cavary project achieved roughly 52 kilonewtons of dry thrust, with a low bypass ratio of 0.16 to 1. The engine was officially delinked from the Tejas fighter program, but the underlying Cavari core technology survived the process. That dry, non-afterburning derivative is now being adapted to power Ghatak, India's autonomous stealth drone. Falling short on thrust was a failure to simultaneously master the material science and physical testing variables, rather than a failure of aerodynamic theory. Jet engines remain among the most tightly controlled and export-restricted components in the global defense supply chain. Achieving autonomy in this domain requires a decades-long accumulation of tacit knowledge and vast, highly specialized supply chains. Blueprints are merely the starting line for aerospace development. Building the domestic ecosystem to cast, cool, and validate those designs represents the true threshold of aerospace supremacy and national industrial maturity.